Welcome to another segment of High School Geometry with Netz and Weichel. This is Mrs. Netz.
And this is Mrs. Weichel.
And we are on our last chapter.
We made it!
Chapter 9.
Woo!
Woo! We're going to graduate from geometry.
Yay!
Yay! All right, Chapter 9, three-dimensional figures, solids. We're going to be looking at, like, how much space stuff takes up and stuff.
I think that sounds like fun.
Well, it sounds like real world to me, but let's get into this. So what are we going to be learning? Well, by the end of class, you will be able to calculate the volume of basic and composite figures. Composite meaning put other stuff together. Why do you need to know this? Well, area and volume are topics that continue at the next levels of math. Optimization questions, area under the curve, volume through rotation are all in later math, especially calculus, like crazy.
Yes.
All right. So how will you know you know it? You will know that you can do this when you can utilize the correct formula given different figures.
Very exciting.
My advice for this chapter, memorize.
Honestly, there's going to be a lot of different formulas you're going to see today, but really, there's like one formula, if I'm being honest. There's slight differences in the one formula from one shape to the next, but it's really one formula.
Base times height.
Base times height. Area of base times height.
Oh, yes.
Area of base times
yes. All right, let's do this. Here we go. So let's start talking about solids. What is a solid? Well, a solid is a three-dimensional object, or we say 3D.
3D.
And your dimensions are your length, depth, and height. You can think of a solid as something that takes up space, or if you were to dunk it in a pool, it would displace water.
It would.
All right. So let's talk a little bit more about the properties of solids. So your very first property of solids is the volume. And you can think of volume as how much water that three-dimensional object can hold, like the amount of water that it would take to fill it up. Your next one would be surface area, and we've already actually talked about surface area when we did surface area. Back in chapter 1, we did surface area with Netz, and I would really like to encourage all of you to revisit that because we will be asking you to calculate some surface area. It's the area that you would paint. And then lastly, the parts of your solids, and that would be your sides, your vertices, your faces, edges, pretty much.
We're going to go into more detail in just a second.
Absolutely. All your parts.
All the parts that make up the solid.
All right, so we're going to talk about two different types of solids. We're going to talk about polyhedra and then non-polyhedra. Ooh. So you may want to add a little side note here. We already did it for you on the non-polyhedra, but add yourself a little side note that your polyhedra, there's no curves. Nothing's curved. Straight, and straight.
I like to think of it kind of like the three-dimensional version of a polygon.
Agreed. All right, so now, if you'll notice, if you're using our guided notes, you have this table, and your table has two different rows. And I would like for you to label those two different rows prisms and pyramids.
So I have them next to each other, but right here, this is your top row. These are your prisms. And then the bottom row for you is going to be the pyramids.
Because there is a difference in these two. And we're going to talk about some differences when we start talking about the different parts of polyhedra. But a little note, think of prisms as something you could drive through or you could walk through. And think of pyramids as, I don't know, they're kind of like the tip of a pencil or something that would hurt if you stepped on it in the middle of the night. Could you imagine?
No, that would hurt. Yeah, I kind of look at the top row you could turn upside down and it would still stand exactly the same, whereas a pyramid, if you turn it upside down, it would fall over.
True that. All right, so let's first talk about our first part of polyhedra, the face. So your face, well, not your face, the face of the face of the polyhedra is, think of the face as it is a part of a polyhedra that you could set it down on a table and it would not roll away. What do you think?
I think that makes sense.
So if it's going to roll away, it's probably not the face. So if you look at a cube, it has 6 faces. If you look at our hexagon.
Pentagonal.
Oh, is that pentagonal?
Yeah.
Oh, yep, you're right. Our pentagonal pyramid. It has 1, 2, 3, 4, 5 triangles, and then the bottom makes 6, so it has 6 faces.
So it's the sides that are flat that you're looking at for the polyhedron. So if you, like when we were doing prisms and pyramids back in chapter 1 with surface area, it was basically all those polygons that you were unfolding.
Yep, absolutely.
In chapter 1, I'm just going to tie in some things from pretty much the first lesson we went over. When we talked about planes, planes were infinite in all directions. Basically, these faces are on separate planes. And if you remember when we talked about planes intersecting, they intersected at lines.
Ooh, those lines we're now going to call
edges. So now we're not talking infinite directions. We're talking about a physical object. So those planes are now just the faces, whereas there's a start and a beginning. So basically where your faces intersect are going to be the segments. And if you're looking at a picture or a drawing, it's going to be what you see. Those segments that you used to make your picture, those are your edges of the three-dimensional figure.
You can also think of it as where would you need, if you had a cube, where would you need to put the super glue for this thing to stay together?
Exactly.
It would have to be on the edges. Can you believe once upon a time our students thought 2 planes met at a point?
We saw that a lot.
We did.
We did.
But now they look at this and they go, that's a line.
That's a line.
I love it.
Yeah.
Okay, so now our third part that we're going to look at is what we call the vertex. Now, here is where we end up with a difference in our pyramids and our prisms. Your pyramids have a special type of vertex, and that is located at the top, and it is called the apex. And you can think of it as where more than 3 faces come together and meet. So, your pyramids...
It's the point opposite your base.
Yep. So your pyramids have this thing called a apex, and your prisms have a bunch of vertices.
And your pyramids have vertices as well. It's just the highest vertex when you're standing it the way it probably should be, where your base is the bottom. The highest point, the highest vertex is more specifically called your apex.
Perfect. All right. Let's talk about those non-things.
So a non-polyhedra is when you have something or a part of it that is curved. So these are all going to probably contain a circle because that's our curved two-dimensional figure. And the first one is a cylinder. So go ahead and fill in the name cylinder above that first picture. Please notice that there are 2 circles making a cylinder.
And your cylinder has some of the parts that your polyhedra does. It does not have vertices. However, it does have 2 faces. Because remember, a face is something you can sit the object down and it won't roll away. Next, you have your cone.
Which looks like an ice cream cone.
It upside down.
Mm-hmm.
So your cone has 1 face, and you can say that it also has an apex. And this is a little bit different in that you don't have more than 3 sides coming together. You just have this one tip there at the top.
Next we have our sphere, which is pretty much what you already knew. It's like a ball.
It's not a circle.
Not a circle.
My lord, not a circle. Please don't call it a circle.
Please.
Not a circle.
Not a circle.
And this one.
This is the most fun.
Not a donut.
Not a donut.
If you tell me the donut-shaped thing, I'm going to tell you that's the wrong answer-shaped thing.
Right.
It's a torus.
It's called a torus.
Absolutely. All right. So that covers our polyhedra and our non-polyhedra. So now let's get into talking about some of our formulas. Now, we're going to first start talking about pyramids is where we're going to start. And please keep in mind that your pyramids are still going to be base times height. But if you think about this, base times height would be you're finding length times width times the height, and that would be if this thing was a prism. But because all those edges lean in, we don't have the whole prism. So all of your pyramids, every single one of them, even your cone, which is a special pyramid, they are all going to be 1/3 the base times the height.
And again, that capital B, where we say the base, we're needing to find the area of that base. So in this case, we have a hexagonal pyramid. So the base is a hexagon. So you are going to need to find the area of that two-dimensional hexagon, which if you remember back in chapter 1, we did this with surface area. Basically, you have to make your 6 triangles and find the area of one of them and multiply by 6.
Please remember that you can use your special right triangles here. And also another formula you remember from a while ago is your n minus 2 times 180, so you can get that one of the interior angles of this hexagon is 120.
Which means this angle right here would be 60.
Because it's half of it. So you know that this is a 30, 60, 90 triangle, and then you can figure out maybe some of the missing sides depending on which dimensions are given to you.
And then over underneath on yours, you guys have more room up and down than I did, so I went left and right. Here is something familiar. This is just review from our lesson 1.5, surface area with nets. Basically, we took the 3-dimensional hexagonal pyramid and just flattened it out. So here's your base and your 6 triangles that would meet up at the apex. So if you remember back to chapter 1, to find the surface area, you would find the area of the single hexagon, and then you would add that to the area of the 6 triangles.
Perfect. Now we have a square pyramid, and we're actually not going to take very much time here simply because it is so similar to your previous pyramid with the hexagon. Again, it's just 1/3 the base times the height. Please keep in mind that capital B means some type of math was done to get that number. In this case, it was the length times the width of the base. And then for your surface area, all you're going to do is calculate the area of the square, calculate the area of the 4 triangles, or just one of the triangles actually, multiply by 4, and then you have your surface area. Now, one of the things I want to mention though is that you name your pyramids by the shape of the base. So this is what we call a square pyramid. And on your previous one, we would call it this is a hexagon, so we would call it a hexagonal pyramid.
There you go. Notice again we did 2 different shapes, both pyramids, but one was a square pyramid, one was a hexagonal pyramid. Notice that the formula is exactly the same, but you have to watch for that capital B. Like Mrs. Nett said, that capital B means almost like a formula within a formula. You have to find the area of that base. Here you would find the area of the hexagon, whereas here you would find the area of the square.
All right, so now let's talk about prisms. Now, a prism. A couple of things I want to mention about prisms. A prism's height is from the base to the top of it. Now with a rectangular prism, this is not that big of a deal because the math works out. However, with some of our other prisms that we'll be talking about in a minute, the area of the base is very important. So when you think about a prism, I want you to think about shipping yourself. What do you think?
Makes sense.
Well, shipping yourself, well, we need a box for you. So
Okay.
we're going to put you in a box.
Okay.
Now, when we put you in a box, imagine if we put you in this box. If we put Mrs. Weichel in this box, she would then be laying down, right?
She would. Yes.
That's fantastic.
She would be.
Did your height change when you laid down? So did you go from, how tall are you? What, 10 or something crazy?
I'm 5'8", actually.
Oh, you look 5'20" to me, but anyway, so 5'8". So when you lay down, are you now like, I don't know,
6 inches.
6 inches tall?
No, I'm still 5'8".
You're still 5'8".
I kind of rotated.
Yeah.
My height is still
Yeah.
the same.
Right. So even when you lay a prism down on its side, that doesn't matter. The height didn't go from being
Your height doesn't change.
Your height doesn't change. So sometimes the height can be horizontal.
The nice thing, as she said, with your rectangular prism, because every single face is rectangular, your
Doesn't
base
matter.
can be anything. So typically, when we look at these, again, you can have any side be your base. I have the bottom here as our base, so we would just be standing up and down. If I wanted, I don't know if I'm hungry. I see like a cereal box here. This is like a cereal box laying on its side. If I were to stand it up, then this would become the base and this would be the height. So you guys have all done rectangular prisms. This is just length times width times height. So commutative properties, as you can multiply in any order. So it really doesn't matter as far as the area of the base, which one you're doing, because you're multiplying all three dimensions together in the end.
Perfect. So with this one, this the prism, the rectangular prism, we already know this one. It's area of the base times the height. You already know this. You've been doing this for a long time. And the surface area also you've been doing for a while because you know that you can flatten this thing out. And here's the cool thing. You really only need to find 3 of the sides. Think of a cereal box. Find area of the front, find area of the side, find area of the top, and then multiply all those by 2 because you have a top, you have a bottom. You have a right, you have a left, and you have a front and a back. So you really only need to find 3 of them, then multiply by 2. If you want to find all 6 and add together, that works too.
Well,
Not
I
a
think
big
a lot
deal.
of you did that when we did these, even in this class, so
No pressure.
no pressure.
All right, so now let's talk about some different types of prisms. Now, this prism is where things start to, the height is important.
Height is very important.
So I want you to think about shipping yourself. And unfortunately, we've broken a leg and broken an arm.
Oh no.
Yeah, and whatever reason, the doctor decided to give you a cast that makes your arms stick out to the side and your leg sticks out to the side. They're just stuck out there. So what would be the best shaped box to ship you in? Well, a triangular prism. Now, if I shipped you in this box, you'd be kind of laying down on your back with your arm down at your side and your other arm sticking out. But this would be a great box to ship you in.
Or even like what I always use when I do this is a 3-ring binder. Think about how would you put your papers in?
Stand it up.
They would stand it up and they'd go in long ways. So for this, the height of our triangular prism, things are going through it this way. Your arm, you're broken. If you're being shipped here, or if your papers, they're all going in this way. So therefore, your height is going to be that way. You have to be very careful because what is our base? It's the triangle. And how do you find the area of a triangle? We use the letter H there as well. So you have to be careful. When we say, like for this, half of base times height, well, that's just of this part of it. What's the height of the prism? This 100% is the height of the prism, which is a totally different dimension. That goes 3-dimensional now from the triangle.
Okay, the other point that I want to try to make for you guys is when you are calculating these, or even when you're calculating the surface area on this one of the things that we like to do is we like to give you some of the dimensions. Like, for example, we'll give you this dimension right here, and we'll give you this dimension right here. But then we'll ask you, we'll have a lot of students that if I tell you this right here is 10, you'll tell me that this is 10 too. But it can't be, because if you look at that top piece is going to attach to what we call the hypotenuse of that right triangle. And you know the hypotenuse is the longest side. So therefore, those two lengths can't be the same. And you're going to have to do Pythagorean theorem to get the length of that one side of this
And
net.
in this case, I feel like it's almost more beneficial to view the net as the 3-dimensional figure because you can actually see, well, you know, this rectangle is connecting here, and then the bottom rectangle, and then right here is your hypotenuse. So you can kind of see, well, that is my hypotenuse side. So folding it back up can be beneficial too.
So now to find the surface area, find the area of a triangle, multiply that by 2 because they match, because it's like a tunnel. And then find the area of each individual rectangle.
I
And
tried to make them differently
Uh,
to show.
mine look all the same. Yours look pretty good. Yeah, you're gonna find the area of each individual rectangle because we don't know. Well, first of all, we know at least two of them are going to be different. So please don't assume that you could find the area of one and multiply by three because then we'll have to assume that you got the problem wrong.
Right, exactly.
All right, so
those are our pyramids and prisms for our polyhedron.
Now let's
shapes.
move on
Now
to
let's
some
go into
rounded some stuff.
the non-polyhedra. So first is the cylinder. The cylinder is with our two circles. So I'm looking for how much can I fit inside here. Early on, we said that basically there's one formula. We need to remember that pyramids are a third of a prism. So for every pyramid with the same dimensions, 3 of them go into one prism. So area base times height. Well, what is the base of a cylinder always?
That it would be pi r squared.
So the area of the base of a cylinder, where are you? There you are. This is basically area of base times the height. It's the same exact formula as it was for a prism. It's just we are guaranteed to have a circle. So rather than using the capital B, we know it's going to be pi r squared.
Now, when you are doing surface area, I would like for you to label, because this one seems to give you all pretty much a lot of grief. I think the public in general just really struggles with this one.
Yes.
So I would like for you to label a couple of parts with the formula that we're giving you. So you know that it's the surface area of the two circles. So pi r squared is one of the circles. I'd like for you to write that on the top circle, pi r squared. And I'd like for you to write on the base circle, pi r squared. You know you have 2 of them, so you're going to multiply that by 2.
So pi r squared for one of them, and then the 2 right here is because there are 2 of them.
Now, I had students ask me, well, why are you multiplying the other thing by 2? Because you don't have 2 rectangles. That's different. So remember, that long piece of that rectangle is the circumference of one of the circles, or actually both of the circles. So we know that to find circumference, you're going to use either 2 pi r or pi d. And I'd like for you to write that along that long piece of the rectangle, so that way you have that. You know that that's 2 pi r. And then to find area, you know you're going to multiply the one side by the other, and the other side is h, or the height of your cylinder.
There you go. And again, you can kind of visualize that here. This would be, I was using a soup can. If you were to take the Campbell's or Progressive soup can label off, you would unravel it from around the can, and what's left is that rectangle. So this is the distance around that soup can. So that's where that whole circumference comes in.
Perfect. Oh, the cone. You know what? They already know the formula.
They do.
They do, because
So
we talked about pyramids, right?
It's the same relationship as a pyramid to a prism.
Well, didn't we say that was like 1/3?
We did.
So
And
1/3 what?
1/3 area of base times height. Well, what is the base of a cone?
Pi r squared.
So there you go. 1/3 pi r squared, which is the area of our base, times the height of the cone.
So we already knew this formula.
We already knew it.
Fantastic. That's one less I have to memorize tonight.
There you go. And then for surface area, we did not do these in chapter 1.
Nope, we did not.
Because this shape is kind of a funky, weird shape. So this is going to be a new formula.
But we're going to do it now.
It's going to be pi times radius, and then that's
the square root of r squared plus h squared.
okay. So there you go. All right. Moving on. And again, these variables are these variables here. So your radius would be right here, and your height would be given right here. You would be given all that information. So just a matter of plugging it into your calculator, honestly, is what I would do.
And to be honest, as far as surface area of the cone goes, your best bet is memorize it.
Yep.
That's where I would go on that one.
All right, and then a sphere. For a sphere, you just have a bunch of circles infinitely going around one single point, basically. So For volume and surface area, you're right here. My radius didn't show up. So your radius is going to be, sorry, I'm going to go ahead and draw this in right now. Your radius is going to be anywhere in the circle, as long as it's from the center and going to a side, because a sphere is all points equidistant from a single point. It's just going in all directions versus just two-dimensional. Be careful with this formula. It's not a difficult formula, but there are some differences. So rather than 1/3, we are dealing with 4/3. Also, for the first time, you have r cubed versus r squared.
Well, and if you think about it, that should make sense because we're finding volume, and volume is cubic. Anytime you raise something to the power of 2, that's squared, that's area, and we're not doing area right now.
Exactly.
Well, for surface area, we're doing squared.
And then surface area is 4 pi times radius squared.
Easy. Let's do some problems.
There we go. So
on the first one, we've got, this is a composite figure. The reason why it is a composite figure is because you have to find 2 different figures to be able to get this done. Now, granted, one of them is being subtracted or taken away, but that's still composite.
So what this is showing is you have this cylinder, but then this right here, this circle, is hollow. So if you're finding just the volume of the object, well, there is no center. So that's what Mrs. Metz was talking about as far as subtracting. We don't really want that to be part of our answer. So the total cylinder, let's pretend like that's not being cut out yet. To find the volume of a cylinder, it's just pi r squared h, where our radius right here is given as 9 meters and our height is given as 3 meters. So we're simply going to plug in that information. Please notice that I have not done anything with the pi sign. You do not want to round, because if you round here, you will end up rounding more than once, and you want to try to limit the amount of times you are rounding, because the more you round, the more distant you get from the actual true answer. Now we have this second cylinder that was cut out of the middle. We know that that cylinder is also going to be pi r squared h. This time our radius is given as 5, and the height, well, you're cutting through the whole thing, we know our height is 3. So we're going to plug in that information. You're simply going to do 5 squared times 3, giving you 75 pi. For the rest of this, you have these 2 volumes. Well, as we've already said, it's almost like we drilled out the middle piece here. So if we took that material away from our original cylinder, we would perform the operation of subtraction. So we're going to go ahead and plug in our calculator 243 take away 75. That is going to give me the exact answer of 168 pi. Now you can go ahead and multiply 168 by pi, the pi symbol, not 3.14, and that gives me a volume of 527.79 meters cubed.
Perfectly easy.
All right, for the next composite figure,
we're going to not subtract this time, because if you look now, we have 2 different solids we're putting together. But one of the solids we didn't talk about.
No, so we'll have to brainstorm with what we can do. So there is one figure that I see, I know we did. I know we worked with this part. That's going to be a cone. I know that for sure. So it's 1/3 pi r squared h, but we don't know our height. Is 13 my height?
Well, if you're leaning over to the side, but yeah, I'm thinking that 13 doesn't go from the bottom to the top.
So I'm going to use the same logic that Mrs. Metz used when she was explaining with the surface area of a triangular prism. The hypotenuse, we know, has to be longer than the other 2 legs. So if this is a right triangle right here, if you look, we have our height, our radius, and then this number 13. That 13 is our hypotenuse. Well, if that's my hypotenuse, then my height must be smaller than that. Well, I know my radius is 5. I don't know my height. I know the hypotenuse is 13. I can just do Pythagorean theorem. And we will try our best. I mean, it's not guaranteed to be a Pythagorean triple. Usually we try to make them that way, but it's not guaranteed.
Yep.
This happens to be a Pythagorean triple. If you know your triples, you already know the height. This is a 5, 12, 13 triangle. If you did not know that, you would just do 5 squared plus b squared equals 13 squared and work it out. You would get an answer of 12. Again, your radius is given as 5, so you're going to simply plug in those numbers. And then from here, again, you don't want to do anything with the pi sign. You want to do a third of 5 squared times 12, which gives you a third of 300 pi, which gives you 100 pi.
All right,
Now let's
that's
talk
great.
about this.
That's the cone. What's that?
So this, it's just a circle on the bottom and it's rounded. So we have to try to think about the shapes we did do. This is definitely not a polyhedron. So we're definitely looking at the ones that had the curved. So
it's not a torus because there's no hole in the middle. Definitely not a
cone
cylinder
because there's no apex.
Well, it's not a cylinder.
Not a cylinder because there's no straight side. So what about a sphere?
Well,
do you think this is part of a sphere?
Maybe like half of it.
Yeah, so let's go ahead and work that out. So we know a sphere is 4/3 pi r cubed. So we know our radius is given as 5. So we're going to plug in 5 for our radius. Working this out, 4/3 of 5 cubed is 4/3 of 125, which becomes 500 over 3 pi. So now let's talk about what we're going to do. We have our cone, and we're adding it to half a sphere or a hemisphere, which is a vocabulary word. So what we're going to do is we're going to take our cone, and we're going to add it to half of the volume of a full sphere. So this is the cone plus a hemisphere. The hemi part is that half part. So if I plug that in, just the numbers, you get 550 over 3. And then if I multiply that by my pi sign, I get that my volume is approximately 575.96 centimeters cubed.
Easy.
All right, so this one is nothing but polyhedra. We have no curved sides, so we have a prism and we have a pyramid. So first, let's look at our pyramid. It's on top here. We know the base is a rectangle, 10 by 4, and then the height of my pyramid is going to be 4. So we are going to simply plug in 1/3 times the area of the base, which is that 10 times 4, and then times the height of the pyramid, which is 4, which is 40 times 4, and then 1/3 of 40 times 4 gives me 160 over 3. Again, please notice this is an exact answer. I did not put 0.3 at all. We're leaving it as exact for as long as we can. Then we have our prism on the bottom here. Our base I'm using is 10 by 4 with a height of 3. So we are going to do 10 times 4 and then times the height of 3, or 40 times 3, which is 120 feet cubed. So we have our two volumes. Did we take away from either of these solids, or are we putting them together?
We're putting them together.
So this is going to be another addition problem. So you're going to take 160 over 3 and add it to the 120 because these are pushed together. That gives you an exact answer of 520 over 3, which is approximately 173.33 feet cubed.
These problems are actually really not that bad.
Not bad at all. All right, this one looks tricky though.
What the heck
I'm a little scared of this one.
that?
So again, when you get a weird looking shape, you just need to find the shape you're familiar with. So if I stop being scared and I really look at this, I see
a pyramid.
I see a pyramid, and then there's that circle that I think is hollowed out. Well, if this circle is hollowed out, and notice those, I see some dotted lines.
A point.
So if I have a circle and it's meeting at the apex of that pyramid, well, I must be drilling out a cone.
A cone?
So we have a pyramid and a cone.
Or a pyramid that's missing a cone.
That's missing a cone.
In the middle of it.
There you go. So this is supposed to be a square pyramid. So we have a square that's our base, and it is 9 by 9. So the area of the base is going to be 9 times 9. Our height, you can see, is given as 8. So we are going to plug in 1/3 times 9 times 9 times 8, which is 1/3 times 81 times 8, which works out to be 216 meters cubed. Now we need to deal with this, the cone. I get asked this a lot. When you're given a diameter and an arrow's just pointing towards the center, that 6 is the diameter of that circle. So make sure if a diameter is drawn and then a number's pointing to the center, you're given the diameter. Well, we know that a cone uses the radius. So if our diameter is 6, our radius must be 3. Because I'm drilling all the way down to the apex, our height is going to be the same as well. So we're doing 1/3 times pi times 3 squared for the radius squared times the height of 8. 3 squared is 9. 9 times 8 is 72, and 1/3 of 72 is going to give me 24 pi. Because we're drilling out the cone, because the cone is missing from our pyramid, we are going to subtract. So you are going to figure out, well, what is 216, which is the pyramid, and then we're taking away the volume of the cone. So that right there is technically our exact answer, because this has pi and this does not. So if you were asked for an exact answer, it is that binomial right there.
There's really nothing else you can do.
So we would just take it to the next level and plug that in our calculator. You should be getting 140.6 meters cubed.
Perfect.
So that is the conclusion of our notes. Hopefully we up the game a little bit with those composite figures. Really, it's just about what shape do you see, and are you adding them together or are you subtracting one away from the other? Other than that, if you can just again remember area of base times height, and that pyramids are 1/3 of a prism. Really, that's all we've gone over for the most part today, other than spheres. Spheres are kind of their own.
Not too bad.
So if any of these gave you some trouble, if any questions occurred and you jotted them down somewhere, please reach out to Mrs. Netzel or myself.
Hey, Mrs. Weigel.
Hey, what, Ms. Netzel?
What's the difference between a diameter and a radius?
I don't know what.
A radius.
Duh.
It's a subtraction problem.
Diameter minus radius would equal radius.
Duh.
Duh. Come on, people. It's funny.
Hilarious.
All right. Thanks for joining us.
See you in 9.2.